Greetings everyone, this is Nila Pandey, and today I'm going to talk about the research work titled as Drone-Based Imaging and Automatic Classification for Glass Facade Condition Monitoring. Now we shall start with the overview of a presentation. We'll go step by step to understand the research work. First, we'll start with introduction and the problem statement. Then we'll talk about our objectives of the project. Then we'll talk about the scope of our work. Then we're going to talk about the literature review, the number of papers that we have been through. Then we'll talk about the actual hardware methodology and software methodology. Then we'll talk about the final outputs. And then in the end, we'll conclude with the future works. As mentioned, we are talking about the glass facade condition monitoring. Our problem is the glass facades are susceptible to defects such as cracks, chips, and discoloration, which can compromise the safety and aesthetics of the building. With traditional inspection methods, it is time-consuming, hazardous, and prone to human error. With our proposed solution, we are planning to use a drone-based imaging combined with automatic defect detection with YOLO algorithms such as V8, V11, and V12. And in final output, we'll use feature mapping to stitch the final output image to improve efficiency, accuracy, and safety for inspections. Talking about our problem statement, we have two main problems during the traditional methods of glass facade detection. First is the aesthetic impact, then the safety compromise. In terms of the issues faced by tall skyscrapers and glass buildings, with more number of chips, the discoloration, cracks, the aesthetic value of the building decreases, and also the safety is compromised. In the same sense, using the traditional inspection methods for tall skyscrapers, the safety of the inspector is also compromised. So with this in mind, we're going to solve these two problems. Our objective is as imaging and defect detection. We have four main objectives. First is the drone imaging. We'll capture high resolution images of building facades, of glass facades. Then we're going to try to stitch them. We'll stitch small images, which are HD images, into a very big image, which will give us a high quality image for the final output. And then we will use the YOLO models, YOLO algorithms to detect the defects in the image. And then finally, we're going to evaluate our models. We're going to use three models mainly V8, V11, and V12. And then we'll compare the YOLO model performances. Talking about the scope of our work, we're going to talk about drone imaging, YOLO models, image stitching, target defects, and limitations. With these five scopes in mind, we'll proceed with our research work. Talking about the literature review, we have been through a lot of papers. We're going to talk about very few important papers here. We have been through a lot of authors and their applications such as surface defects in glass, flat panel display defection, crack detection, or even crack detection in concrete structures also. This helped us to understand the traditional methods and what can we contribute as in the new research work. In this second literature review slide, we explored the deep learning for defect surface detection. We used deep learning for deep learning for glass bottle, and then surface defect detection methods. And also we researched on the faster RCNN methods for the defect detection because we wanted to optimize our model as much as possible. Now talking about the methodology, we have used a very basic and very simple methodology method, which is first we're going to work on data collection, then YOLO model development, and then finally we're going to talk about image stitching and defect detection. We have captured over 800 images of glass facades using a drone in University Technology Petronas campus. We have shortlisted 123 unique images with unique features to annotate them with defect labels. We have applied YOLO models for defect classification. We have used three YOLO models, V8, V11, and V12. And then finally, we are using Shift and Ransack to stitch multiple drone images, mostly 35 drone images of a single building. Then we're going to combine them and make a very big image with high quality features of that one side of the building and a single panoramic view. We're going to talk about all three stages in next three slides. Beginning with the data collection, we use the drone, which is the DJI Neo drone, equipped with the 4K R camera. We have captured over 800 images from multiple angles and heights to ensure that we have full coverage of the glass facade. Then we used only 123 unique images with unique features to annotate them for defect labeling. We use defect labels such as bad glass, decent glass, dirty glass, good glass, bad paint, cracks, or rust in terms of metal, good metal, bad metal, such as these. Then we use pre-processing. We resize the image and use argumentation such as flipping, rotation, and brightness adjustment to enhance the dataset diversity. And then we splitted the dataset into train, test, and valid for model development. And then finally we use the dataset for image stitching and YOLO based defect classification for automated facade monitoring. Talking about the three YOLO model development, YOLO model V8 performance. It performs well for detecting large defects but struggles with the subtle defects such as decent glass and dirty glass. The difference between these two types of glasses. For YOLO V11, it improves the precision for detecting bad glass but has a lower recall for decent and good glass. And YOLO V11 outperforms both V8 and V11 in accuracy and recall. It is the best model for detecting wide range of defects, especially the bad glass. In the right side, you can see the difference in all three approaches of YOLO versions. And in this way, we have used all three versions of YOLO and compared them simultaneously for their output. In the final stage of our methodology, we're going to talk about image stitching and defect detection. As you can see in the right side of the flowchart, first we use the input images and then we extract the features using shift, which is scale invariant feature transform. Then we use random sampling consensus to track down the features in each of the images. Then we use image alignment and bundle adjustment. At the end, we blend the images to get the final panorama. Here you can see a below example in which it is 35 separate overlapping images of a building. We have used shift and ransack to map the features of each overlapping images, and then we're going to use the image alignment and bundle adjustment to generate a full face panoramic image of the entire facade. Talking about the final output, as we have previously mentioned, YOLO V8 has lower performance compared to YOLO V12, especially for the smaller defects. For the larger defects, it was able to detect them. For YOLO V12, it is the highest performance with more than 70% MAP on the test set. YOLO V12 showed moderate improvements over V8, but still lagged behind YOLO V12. In the end, talking about the model performances again, V12, as I mentioned, it achieved performance with more than 70% MAP on the test set, best model for defect detection and classification. V8 and V12 has their own disadvantages and advantages, but YOLO V12 outperformed them. In terms of image stitching impact, image stitching was critical in providing a complete panoramic view of the facade and enabled more accurate defect classification by capturing the entire surface of the building. With this final stage of the methodology, it helped us to make sure that the person responsible, the inspector, will have a clear view of the building, and they should know where and which defect is detected in which place of the building. Here in this slide, we can understand that why image stitching was very crucial to our project. As you can see, with so many the above image, the first image, it is a combination of 35 single images, solo images, and then we have used the feature mapping, the overlapping features in those 35 images, and then combined them. And here in the below, we can see the output which we have put in YOLO V12 model, and it is able to detect clearly which glass is of which type. Talking about the final output in terms of table, as you can see, V8, V11, and V12 we have used. V12 outperforms both the models. Then V8 and V11 has some improvements. As you can see, for MAP at the rate 50 test, YOLO V8 has 62%, YOLO V11 has 55, and YOLO V12 has 70. But as you see the precision test, in that we have achieved 90% accuracy. YOLO V11 has 91, and then V12 has 92. With recall test, V8 performs at 36%, V11 has 24, and V12 has 36. V12 all outperforms both the YOLO models, V8 and V11. I like to conclude that with this research work, we developed a drone-based system combining YOLO models and image stitching for glass facade monitoring. YOLO version 12 was found to be the most accurate model for research real-time defect detection. In terms of future work, we can optimize the YOLO models for better recall and smaller defects and integrate real-time processing for on-site monitoring. With this below flowchart, there is a roadmap for the future works, such as developing drone systems, implement YOLO models, identify YOLO as the best, and then optimize YOLO models and then integrate the real-time processing. I would like to thank to the panel for seeing this presentation, listening to my presentation, and thank you so much for everyone who has supported us through the research work. Thank you so much.